All right, let's recap. We had mechanism. For ozone depletion. Our book says destruction, and it's probably right because it's making actual ozone molecules go away. Depletion is more of a big picture word of, hey, I've got lots of ozone, and then I'm going to deplete it and have less of it left over. All right, so we've seen this thing that we're going to go ahead and call mechanism 1. And it is some reactive species X. We talked about what X is likely to be, but there are exceptions. And it's going to react with ozone, and it makes an oxide of X and then generates oxygen gas. And our book doesn't use state symbols to describe that this is all occurring in the gas phase. That doesn't mean that we shouldn't. And then our non-metal oxide gas reacts with a reactive atom of monatomic oxygen in the gas phase. And that frees up X again. And we have an overall reaction. So there are two things going on. X here is catalytic. It gets consumed by the first step, but then gets regenerated in the second, so it can go back and do the damage again. This is a chain reaction. If you just look at what X is doing, X gets consumed, it goes away, and then it comes back. And so this, at the end of line 2, can go back and feed back into 1. This is what we call a chain reaction. So a very small amount of X can just keep churning away and use ozone as its feedstock, and could consume dozens of molecules, hundreds of molecules, thousands of molecules of ozone, until it somehow gets degraded and goes away. But because the X is on both the left-hand side and the right-hand side, when I add these two lines together, it doesn't show up. It's catalyst. And XO is made in the first step and consumed in the second, so it's a reactive intermediate. It also doesn't show up in the overall reaction. What we have as an overall is that ozone and monatomic oxygen makes 2 molecules of dioxygen. And this works. We can follow it. It makes sense, but there is a problem. There is a problem. And the problem is this guy. There's not a lot of monatomic oxygen in the atmosphere. So this is only available in low concentration. And if you have a quick read of the book, it says, at specific altitudes in the atmosphere, this number is going to vary. And at the place where we're seeing the most significant, most substantial amount of ozone depletion, this is really at a very low concentration. So this mechanism probably isn't the big one. This is a cause of ozone depletion, but it's only one of them. There is another one. Let me see if I can find that paragraph for you. Mechanism 1 requires atomic oxygen to complete the cycle. But the amount of atomic oxygen that is in the lower stratosphere between 15 and 25 kilometers. So we have very low concentration of this between 15 and 25 kilometers. So if there's another mechanism that does something to ozone but doesn't include the requirement for that dissociated monatomic oxygen atom, then we should probably consider it. And there is another one.
Quick question.
Yeah.
What is considered a high concentration?
Well, remember Tuesday we did a calculation out of the book, including what its concentrations came from. And even those they sounded like big numbers. They were like, hey, I have 1 billion molecules per milliliter. They were fairly large numbers. That turns out to not be a lot in terms of moles. In the chemistry world, when we're talking about concentration, we talk about moles per liter, right? Our book said molecules per cubic centimeter. So, in order to be 1 mole, Avogadro's number says that in a liter of gas, you need 6.023 times 10 to the negative, times 10 to the 23. That's a 6, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That many zeros. So when we have a mindset that thinks that 1,000 is a big number, and that 1,000,000 is a big number, and that 1,000,000,000 is a really large value, we're nowhere near close to figuring out what's concentrated. Okay. So even if I had 1,000,000,000 molecules in a cubic centimeter, and there are 1,000 cubic centimeters in a liter, I would only have this many. I would only move to here. So in terms of moles, it would be 0.000000000. So still really, really low in concentrations. Our gas concentrations in the atmosphere are going to be low. The fact is, though, there's a lot of it. The atmosphere is big. We were talking the other day, just outside of the table, and I said, has anybody got any idea how heavy a cloud is? You know what cumulus clouds are? Those are the fluffy ones. Cumulus means like stuck together. So we've got there's 2 types of big fluffy clouds. There's nimbus, the big cotton wool clouds, and then cumulus, big clouds. And a cumulus cloud can be a kilometer by a kilometer by a cubic kilometer. How heavy is the cloud? You can give it to me in any form you like. I'm going to give it back to you in tons.
I'll say like
50 pounds. A cloud, I mean, it's a big fluffy cloud, right? You can fly through it. You can There's videos out there on YouTube of skydivers diving through the cloud, right? About 400 tons. There's 400 tons of rain in a big cloud. Yeah. So, and that's water that is still so finely divided that it hasn't turned into droplets that are big enough yet for gravity to act on them and pull them to the ground. So it hasn't even turned into rain yet. So, when we think about the atmosphere, it's not like in lab where I have a beaker and it's got untold trillions and trillions of molecules in it and another beaker, and I mix these two liquids together. The gases, if this is a gas atom or a gas particle or molecule, its next nearest neighbor is all the way over here, which makes them dilute. The chances of them interacting is slim, but real, because, hey, they meet each other and they collide. These have to meet each other and collide with each other before the reaction can happen. And there's so few of them. But the sky is very big. The atmosphere is very big. There's lots and lots of volume in the atmosphere to make up for the fact that concentration is low. Can I move that out of the way? There you go. All right, so we need another mechanism that doesn't require me to have this item. I'm going to call this a mechanism 2. And mechanism 2 feels largely the same as mechanism 1. I have this item, X. Our book just calls it X. We talked on Tuesday about what the huge culprits in the environment are. Chlorine, bromine, and some nitrogen oxides. But we're leaving our options open. This reacts with an ozone and forms XO, some non-metal oxide, and makes oxygen. And we also spoke about, again, on Tuesday, ozone is a high energy molecule. It's an unstable molecule. But dioxygen, O2, with the double bond between those oxygen atoms, is a very, very stable molecule. So ozone is looking for something to react with, to turn into oxygen. It's looking to give one oxygen away. Okay, this still gets to be line 1. Line 1 in this mechanism is the same as line 1 in the previous mechanism. But now, I get a second line 1 as line 2. I'm going to do it twice. I have some as yet unspecified chemical X. Probably a chlorine, possibly a bromine, possibly a nitrogen oxide of some form. Okay. And then line 3 follows. Now, if we have a culprit atom or molecule in the atmosphere that is capable of doing line 1, there's every reason to believe that you just get 2 of them. That this line and that line are the same thing. But there will be times when there's chlorine and bromine both available in the atmosphere, and line 1 and line 2 are not the same thing. Okay, so what our book does to distinguish this, and we do this in other branches of chemistry too, is just put a little prime mark there, a little apostrophe that just says these do not have to be the same as each other. Okay, X can be the same as X prime, or it could be different. Chances are they're the same. Chances are they're from the same family. One's a chlorine, one's a bromine. But they could be different. Our book doesn't want to commit itself to anything. Okay, and then we get line 3. And line 3 makes up for the fact that I don't need this guy anymore. So I'm going to take my oxide, XO, and my other oxide. If they're the same thing, you just say 2 XOs. If they're different, then they're different. And this makes X. And the other one, so it could be 2. If this is chlorine oxide, it would make 2 chlorines and oxygen gas. Okay, remember, oxygen gas, this guy. This is very, very stable. This is the key here. Oh, maybe time for a new pen. That guy, this is a brand new pen. It hasn't come in yet. It just hasn't come in yet. I took that out of the box yesterday. Oxygen, group 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm going to make a bond here, make a bond there. Double bond. Okay? The fact that it has this double bond makes it be 21% of the Earth's atmosphere. If it's abundant, that must mean it's stable. If it was reactive, it couldn't be this abundant. And again, I'm making it really here. So this is the key. The key is that we take reactive, and we end up with something that is not, that is stable. Okay? All right, let's do the overall for this.
Quick question.
Yeah.
For mechanism 1, the first 2 steps were called the elementary step.
Yes.
What would this one be called?
They're still elementary steps. Yeah. If X is the same as X prime, then we could say that the elementary step could be, for the mechanism 2, could be 2 steps. That 2X plus 2 O3s make 2 XOs and 2 O2s. Okay. Because I need the 2 XOs to make 2 X's plus O2. Okay. All right, let's see if we can do the overall again. Are we comfortable with how to combine reactions together, group all of the reactants on one side, group all of the products on the other side, and then cancel anything out that appears more than once. All right, let's do it. Let's do it. It's on the video from Tuesday. Let's do it again. The arrow is an equal sign. Everything that's on the left-hand side has to equal what's on the right-hand side. It's the law of conservation of mass, okay? Number of atoms on the left have to equal the number of atoms on the right. So you write down everything. Put it all on one line, okay? So, X plus O3 plus X prime. And putting the gas. If you don't put the state symbols in, no one cares at this point. You've got a long way to go, right? Plus O3 plus XO plus X prime O. All right, that's everything that's on the left-hand side of this equation. On the right-hand side, XO plus O2 plus XO plus O2 plus X plus X prime plus O2. Okay? You write absolutely everything out. So these individual steps, 1, 2, and 3, these are what are called elementary steps. And our overall is line 1 plus line 2 plus line 3.
How many lines? What's the max amount of lines you can have?
You can have as many as you like. I don't think that there's a physical limit to how many you can have. How many could be described easily? 2 is easy, 3 is doable. 4 and 5, people start losing track of what the variables are. It doesn't mean they don't exist. It's just that we haven't kept track of them. And in one of the blue boxes of, the book has the major points of the text on white pages, but then it'll have like I can't tell whether it's blue or green, a blue page where it says, hey, here's how we're going to apply this information. There is one that's, is it 5 or 4? It's 4, but one of them's that you could easily include an extra 1. Let me see, 4, page 31. There is a 4-step thing going on. All right.
You've done. What's the most you've done?
Probably 3. Yeah. Okay. That's an equal sign. If you're on both sides of the equal sign, you've got to go X.
Yes.
This X appears on both sides of the equal sign. It's got to go. O3, ozone.
No.
No. X prime.
Yes.
Got to go. O3.
No.
Nope. XO. most of what we've written down goes away. Which then gets to be, I have an O3 and an O3. Makes an O2 and an O2. Oh, and an O2. And again, when you look at the overall reaction, we saw this on Tuesday, when you look at the overall reaction, it tells you nothing at all about what's been going on. This reaction, if you put some ozone in a container and you seal the container, when you come back, it hasn't turned into oxygen. It hasn't. This does not happen on its own. It has to react with X twice. X is a generic non-metal term. There's no X on the periodic table. And then we make these guys. And those guys react with each other and regenerate what we started with, and then form the product. So if we're going to label what we're looking at, that O2 and that O2 and this O2, they are all products. This O3 and that O3 they're the reactants. They're the things that make it through to the final answer. That my ozone turns into oxygen, dioxygen. Now there's a couple of things along the way that are doing all the heavy lifting, but they don't get to show up in the final answer. What's the role here of X? X, the reaction doesn't work unless X is present. X gets consumed in the first step, but then gets regenerated at the end. So the reaction doesn't work without it. It's used but not consumed. What word in chemistry do we have for that?
Reactive.
Not this one. That's a catalyst. That's a catalyst. X is a catalyst. It gets used but not consumed. There's every reason to believe that X and X prime are the same thing. And I can even write that one down for you, where mechanism 2 is that this is the same thing. It would just be 2X plus 2O3 makes 2 XOs and 2 O2s. So X and X prime are both catalysts. The reaction needs them in order to progress, but it does not consume them. All right, let's look at this guy. I'll put 2 lines underneath this one because I've only got 3 colors. This one gets made early on by reaction number 1, but then gets consumed later on in step number 3. What? That's a reactive intermediate, yeah. It is very common for reaction mechanisms that are step-by-step sets of instructions to have something that pops up in the middle of the reaction but then goes away again. Okay? And because this one gets made but then immediately consumed, it never shows up in the final answer. That's a reactive intermediate. Okay. I'll rewrite this just for the sake of doing it.
Is there a mechanism 3? I mean,
No.
3?
If there is, I'm unaware of it. There probably is. There's probably 3, 4, 5, 6, 7, and 8, but these two seem to be the big two. All right, so mechanism 2. I'll tell you what, you do it. What would mechanism 2 look like if X is equal to X prime? What's likely to happen here is that X is a chlorine atom. Our book is holding back on blaming chlorine. The answer is it's chlorine. Chlorine is the big culprit, but it's not the only one. Our book is holding back from saying it. Okay, I'll tell you what. Let's actually go out and say it. X is equal to X prime. And X and X prime are both chlorine atoms. What would my mechanism look like? Here, line 1 and line 2, if you're doing mechanism 3 in 3 lines, line 1, line 2, and line 3, line 1 and line 2 get to be the same line. So you can combine them into one thing. Go ahead and give yourself a chance of doing that. In fact, you want to do it together? Do it together. So I had line 1, line 2, and line 3. Line 1 and line 2 are only needed if the identity of the atom causing the initial ozone to cleave is different from in line 2. If they're both the same thing, and in this case I want you to make it be a chlorine, if they're both the same thing, then line 1 and line 2 are the same thing. If you write them both out separately, fine. But you'll realize that it's the same thing twice, so just put a big 2 in front of everything.
Okay.
Yeah.
And then line 3 is different.
Line 3 is now line 2. It will be the same concept as previously, but its X is now replaced by Cl. Wherever there was an X, that X is now Cl. Okay? Chlorine, and to a lesser extent bromine, are the big culprits of chewing up ozone in the atmosphere. One of the problems is, there's more chlorine in the atmosphere than there is bromine. But bromine does this better than chlorine does. It's many times more effective at this reaction. Our book says something like 50 times better. But there's also very little bromine up there.
Yeah. Yeah, so it's still
If you write line 1 and line 2 and you replace X and X prime with CLs, you'll realize they're both the same line.
yeah.
And you can collapse that down to something that is twice as big, because line 3 requires 2 chlorine oxides. Requires 2 of them. You have it?
We're on the third line.
Okay.
So I guess it should be CL, right? Just for this X. Yes. I think we got it.
Okay. So working on the assumption that mechanism 3 should be a 3-line mechanism, I've replaced X with Cl. So I have an atomic gas for chlorine. And the other reagent, the other reactant is an ozone, and it makes chlorine oxide and O2. And then line 2 states exactly the same thing. Exactly the same thing. Okay? So what I'm going to do is just say, I have 2 of these. And I have 2 of those. And I have 2 of those. And I have 2 of those. Okay. And what we'd be tempted to do in chemistry 1, in fact we tell you to do this, is there's a better answer to this. Just divide everything back by down to 1. Because everything on this line has a 2 in front of it. Therefore, you can get away with it saying 1, right? We don't want that because I need 2 of these in the next step. Written out the way that it was previously, it said XO plus XO makes actually no, all right. It said X plus X prime plus O2. Okay. All right, well, let's simplify this line. So that was X, the XO and X prime O makes X and X prime plus O2. These are the same thing. These are the same thing. Okay. Take everything that's on the left and add them together with everything that's on the right. I have 2 CLs and 2 O3s and 2 CLOs, making 2 CLOs and 2 O3s and 2 CLs and 2 O2s. And those chlorines cancel with those chlorines, And these chlorine oxides close with those chlorine oxides. And we get the same answer. This is the answer. Okay? But, again, it tells you absolutely nothing. It doesn't tell us what's causing this. And the thing that's causing it is atmospheric chlorine. Okay, so there's a multiple page, there's a 4-page blue-green text where it says something quite important. In mechanism 1 and in mechanism 2, something happens. X goes away and comes back. Goes away and then comes back. XO is made, but then goes away. And then is made and goes away. And then is made and goes away. This is a chain reaction. This gets consumed, but then is made again. And so it can loop back into line 1 and go again. So if we were to track concentration versus time, here's time. Square brackets means concentration. And I'm going to label 3 things. This mechanism's a little bit easier than that one, but what I'm about to say is applicable to all of them. I'm going to label X in red. I'm going to label ozone in black. And I'm going to label the oxide in green. I'm going to plot a black line, a green line, and a red line versus time. Which one do you want first? Red, black, or green?
Do green.
Let's do green first. What happens to the concentration of green over time?
Concentration gets lower.
You picked green. Here, at the very, very beginning of the reaction, green doesn't exist. So on my graph, green does not exist. There is no green. And then I make some of it. This is a product. It's on the right-hand side of the equation. But then it very rapidly goes away. And then it gets, and then, because this regenerates itself, it makes more green and then destroys green. Makes green, destroys green. Makes green, immediately destroys green. On this graph, where's the green line? We know it starts at 0. Is the concentration of XO, the green, ever large? Does it ever get to be a big number? No, because as soon as you make it, it goes away. So green does this. It pops up, but then steady state. It's being made and consumed and made and consumed and made and consumed in a reaction that goes around and around and around in a loop. We know that there's none at the beginning,
So,
and then the concentration during this reaction, it never needs to get big.
so all reactive intermediates are steady state.
That's more or less safe. It's a safe-ish assumption, yes. Yeah. You make them, they go away. You make them, they go away. All right. What do you want to do next? You've got black and red left to do.
We could do the red.
Red. Look at this. At the beginning, there is red. So red does not start at 0. Green started at 0. Red starts at some amount. And then you make it go away and it comes back. And you make it go away and it comes back. And you make it go away and it comes back. And you make it go away and it comes back. What does the line for red look like?
Maybe the opposite of the green one. Starting somewhere,
It has to start somewhere.
but not as.
Let's put it here. For every one that you remove, you generate one. It also stays the same. It's a catalyst. It's required for the reaction to work, but it does not get consumed. Its concentration does not diminish over time. That just leaves us the black line. So we had called the red catalyst. We had called the green reactive intermediate. This green doesn't have much more ink left in it. The black box, the black square, needs a name. We should give it a name. It's not going to be a name that our book uses. I'll be surprised if it does. I'm going to use the industrial word for this. This becomes what we call feedstock. This is the stuff that gets consumed. You start with ozone, and it's not in the final product. It goes away.
So from a product to nothing, mixed to.
What does that look like? I'm going to include a trace of what the black line does. What does the black line look like? It starts with the real value. And then it's gone. It goes away. Our overall, this is the first time that we've been able to use it, says you start with some ozone and you end with none. So given enough time, this reaction will consume all of the ozone. What's that going to look like on a graph?
It'll just be a dot.
It's going to be a what?
Just a dot and the
Okay, so
x-axis.
we have to start at a real number. Here's my real number. What happens next?
It goes for a little bit.
Okay.
And then it disappears. Then it stops.
And then bam, like that. It goes for a bit like that. Do you remember the day that we brought the marbles in and shook the marbles?
Yeah.
What was that about?
Mixture.
Making a mixture. Gases are mixtures. What specifically about a gas mixture were we trying to simulate or replicate?
Which gas?
No, the process. Looking for a word. Begins with D. Diffusion. Okay, here's the deal. If at the beginning of your reaction starts with lots and lots and lots of reactants, your reactant is called A. At the beginning, there's lots of A. And as the reaction goes, A, boop, turns into B. B's your product. A, boop, meets another A, whatever, boop, and they do reaction, boop. And over the course of time, boop, boop, more and more A gets turned into B. Okay, we're not quite halfway through yet. Okay, we're about here. Have I made it easier or more difficult for A to react?
Harder.
Yeah, yeah. The fact that now A is in the presence of things that are not A, this one here is surrounded. Look, there's a B there and a B there and a B there. It has to diffuse to the other reactants in order to do the reaction. So as a reaction progresses, it finds it more and more hard to find other reactants to react with. At the beginning of a reaction, wherever it looks are reactants. So at the beginning of a reaction, the rate is quick. And then over time, it steadies out and curves away. That's normal behavior. This is complicated a little bit by the fact that there's a catalyst in here. And the catalyst is taking things, breaking them, and passing them on. Taking something, breaking it, passing it on. And it itself is getting regenerated when that happens. So this line that under normal conditions we would expect to curve and go away to almost zero might actually flatten out. And we would have to do the experiment to see what's happening here. But it might find a rate where it just keeps doing the same thing. Okay. If you have an unlimited amount of this, maybe it finds its own pace and then just keeps churning. Okay. All right. That 4-page blue text that runs between page 30 and page 33 is fairly technical. It talks about reaction rates, it talks about multi-step processes and reaction rates. I think that we skip it for now, and if what's in the next chapter highlights it, we'll come back to it. Okay. The next chapter out, it's only chapter 2, is about the ozone holes. Okay. It takes its while, it takes its sweet time to get there, but somewhere around page 54, chemicals that cause ozone destruction is the first time that it says chlorine. The answer is chlorine. This thing is chlorine. Now, there's a very, very small amount of naturally occurring chlorine in the atmosphere, but the chlorine that we're worried about came from a particular type of man-made chemicals. These chemicals were the wonder chemicals of the 1960s. When we made them, they were fantastic. Let's look at that on Tuesday. So the next chapter is much, much more descriptive. It talks about climate and the holes being at the poles and what caused them and how we should probably go ahead and regulate that. Okay, so not a science chapter, more of a discussion chapter. Okay, see that on Tuesday.
Cool.